Welcome to Theory of Computation. This is lecture number 31. Well, we've been discussing the theory of NP-completeness, and what we're doing is we're taking concrete problems and we're proving that they're NP-complete. If we look at what we have done so far, we proved the Cook-Levin theorem, which told us that SAT was NP-complete. After that, we looked at this problem called 3-SAT, and we proved that 3-SAT was NP-complete by reducing SAT to 3-SAT. After that, we looked at a problem in graph theory called the independent set problem. In the independent set problem, you're given a graph and an integer k, and you're asked if this graph contains an independent set of size k. An independent set in a graph is a set of vertices such that there are no edges between any two vertices in this set. So an independent set is a bunch of vertices such that if you look at only those vertices, then the induced graph is empty. You will not see any edges going between any two vertices in that set. So given a graph, to be able to tell whether it has an independent set of size k or not is also NP-complete. Well, let us not lose focus and let's think about what NP-completeness tells us. NP-completeness tells us that a problem is difficult to solve. It gives us very, very strong evidence that there might not be a polynomial time algorithm for it. So you may ask, what is the use of proving that problems are difficult? What is the use of hardness results? NP-completeness results are actually hardness results. They point out that a problem is difficult by saying if you solve this one problem, you'll solve many other in polynomial time. So what's the use of proving that a problem is difficult? Well, this has an extremely important practical use. Suppose you were given a problem which came from some question that arises in databases or operating systems or any other branch of computer science, or it could be any other problem, and you worked really hard on trying to find an algorithm that would solve this problem efficiently. Now suppose that you tried and tried and tried and failed. You were not able to find any efficient algorithms for the problem that was posed to you or the problem that you wanted to solve. Well, if there was no theory of NP-completeness, if there were no hardness results, then you would just be stuck. You will continue to work on this problem and continue to spend more time on this problem. On the other hand, if you've spent sufficient amount of time on a problem and you can't find a polynomial time algorithm, now what you can do is look at the theory of NP-completeness and ask yourself the question, well, maybe the problem that I'm working on is NP-complete. And then what you can do is you can try to prove that your problem is NP-complete. If you can establish that your problem is NP-complete, that does tell you something about the problem, something very important about the problem. It tells you that your problem is so difficult that if you are successful in solving it, you would solve all NP-complete problems. Most computer scientists are not skilled enough to handle or tackle such deep questions. In that case, most computer scientists who are practical minded would just stop searching for a polynomial time algorithm for that problem. And they'd say this problem is very difficult, it belongs to the class NP-complete, and they will try to either circumvent the problem or look for what we call approximation algorithms for that problem. Well, the point is that once you realize that a problem is difficult, that realization would allow you to search for alternative strategies. But if you were to never know that this problem is so difficult, then you would continue to spend a lot of time in the wrong direction. Most people do not want to work on the P versus NP problem. So people do not want to look for polynomial time algorithms for NP-complete problems. So establishing that a problem is NP-complete is telling a lot about the problem that we are working on. Well, last time what we did was quite spectacular. we looked at 3-SAT and then we looked at the independent set problem. And we showed that the independent set problem is reducible to 3-SAT. This established that the independent set problem is NP complete. We already know that 3-SAT is NP complete. Now, what does this tell us? This tells us that any satisfiability question can be reposed, retranslated into an independent set question, and vice versa. So you can think of working with two languages, and here I don't mean languages in the formal sense that the way we define languages, but language in terms of the everyday use. You can think of two languages. One is the language of independent set problem. In that language, all you're allowed to do, the way you speak in that language, is you present a graph and you present an integer, and the only question you can ask is whether this graph has independent set of size k. You can think of the other language, which is the language of satisfiability. In this language, the way you speak is you present people with Boolean formulas, and after presenting them with Boolean formulas, the only question that you're allowed to ask is whether the Boolean formula is satisfiable or not. Well, what we have seen is these two problems are polynomial time equivalent. What that means is it is possible for us to translate one problem into another very quickly, and we can translate it back. So these two, there is an efficient translation scheme between these two problems. So in some sense, translating these two problems from one to another is not very difficult. However, remember that when you say that two problems are polynomial time equivalent, you're not saying anything about the individual complexity of either of the two problems. What you're saying is something about the relative complexity of both the problems. So you're saying these two problems have relatively the same complexity. You have said nothing about the individual complexity of either of the problems. The two problems that are polynomial time equivalent to each other may be very easy, they may be polynomial time solvable, and they may be very difficult. They may not be polynomial time solvable. So that's what we are doing. Our focus is now we're collecting problems that we suspect are hard, and we're building evidence that they are hard. As more and more problems are included in the class NP complete, what will happen is we will become more and more convinced that these problems are genuinely hard. Once again, this would be very strong evidence. As the class NP complete grows and more problems are added to it, and we realize that these problems have come from different branches of computer science and mathematics and other fields, and that people have really tried to find polynomial time algorithms for not one NP complete problems but so many of them, and they have failed. That gives us evidence that these problems are genuinely hard. But for us to actually believe that, we would want the class to see that the class NP complete does contain a lot of different kinds of problems. Well, last time we also looked at a new problem in graph theory which we call clique. For us to understand this question, we'll have to first understand what a clique in a graph is. Well, let's take a graph and let's look at a subset of vertices of this graph which has the following property. If I look at any two vertices inside the set, I realize that there's an edge between them. If that is the case, then I'll call such a set a clique inside a graph. So a clique is a complete subgraph of a given graph. It's a subset of vertices such that if I only look at the graph induced by those vertices, I realize that I'm seeing the complete graph. So a clique is going to be just a subset of vertices such that every vertex is connected to every other vertex in the subset. Now, if I give you a graph and integer k and ask you if this graph has a clique of size k in it, that turns out to be an NP complete problem. To formalize this computational problem, we define a language. Let's go ahead and do that. Let us define the following language, clique, which is the set of all pairs g, k such that g has a clique of size k. So computationally we have a problem in which we'll be given a graph and an integer k, and we have to find out if the graph g has a clique of size k in it. So this is the computational problem. What we want to do is we want to show that this problem is NP-complete. Once again, we recall the definition of NP-completeness and realize that we have to show two things. The first thing we have to show is that this problem belongs to the class NP. How will we do that? Well, it is very easy to give a verification algorithm for the clique problem, and this was your homework last time. So we will not spend time on proving that this problem is in the class NP. That's rather trivial, and it's your homework. It was your homework, and I'm sure you've done it by now. But today we will just prove that this problem is NP hard. So how will we go about it? The problem that I have chosen, this clique problem, well, we'll see that the reducibility that eventually we will come up with is not going to be very difficult. But what I want to do is conceptually clarify many things for you by taking this simple example. We want to show that clique is NP-complete. What we have to do is we have to ask ourselves, what are the problems that we know are NP-complete? Or we should really be asking ourselves, what are the problems that we have already proved to be in the class NP-complete? Well, there are three problems. One of them is SAT, the other is 3-SAT, and the third one is the independent set problem. So far that is the knowledge that we have gained about the class NP-complete. Now, what we can do is, to show that clique is NP-complete, we have three alternatives. We can take either SAT and show that it's polynomial time reducible to clique. We can take 3-SAT and show that it's polynomial time reducible to clique. And we can take the independent set problem and show that it's polynomial time reducible to clique. So the question is, which one of these problems should we choose? See, as our knowledge of the class NP-complete increases, so do our choices. Remember, to show that a problem is NP-complete, and let's say we already know that the problem is in the class NP, all we have to do is take an NP-complete problem and reduce it to our problem. As the class NP-complete grows, or as our knowledge grows, remember that the class NP-complete doesn't grow. It's a well-defined mathematical object, and so it remains the same forever. It's a precisely defined thing. But as our knowledge of the class NP-complete grows, what we can do is we can choose any NP-complete problem and reduce it to our problem. And for the clique, once again, we have three choices. The question is, which one should we choose? Which out of the three reducibilities, which one should we try to do? The answer to that is, well, in theory, you can do any one of them. It doesn't really matter. But in practice, what you should do is you should choose the problem that looks fairly close to your own problem that you want to prove is NP-complete. So let's think about it. We are working on the clique problem, and we have three problems that are known to us which are NP-complete. Two problems are from Boolean, or are concerning Boolean logic. They are satisfiability questions. The third problem is a graph theory question. So it seems to me that if I were to try to prove that clique is NP-complete, I would first pick the graph theory question and see some similarity between that question and my question, because I know that clique is also a graph theory question, so they should be close to each other. So when you are trying to prove that a problem is NP-complete, always pick one that looks closer to the one that you want to prove is NP-complete. Let's continue. So what we do is we choose the independent set problem, and now what we want to do is we want to reduce the independent set problem to the clique problem. How do we reduce the independent set problem to the clique problem? Well, for that what we'll have to do is think about both these problems. What we should do is start thinking about both the problems and try to find some similarity, some relationship between the two problems. If we can find some relationship between the two problems, it would help us in coming up with the reducibility from one problem to the other. So let's look at clique and independent set and see if there's any relationship between the two concepts. So what is the relationship between independent sets and cliques? That's the question. The answer is very simple. Let us say G is a graph, and let us define the complement of the graph, G bar, which is going to be a graph on the same vertex set, except for the edges are going to be the ones that are not edges in G. So, to define the complement of a graph, if you have a given graph, it has some edges in it, what you do is to take the complement of the graph, you throw away all the edges which are in the graph, and whatever edges were not in the graph, you put those in, and you get the complement of the graph. Now, here is the simple relationship. The graph G complement contains all the edges that are not in G. So let's look at this concept using this figure here. Here we have a graph G, and on the side we have drawn a graph which is the complement of G. As you can see, all the edges which are in the graph G are not in the graph G complement, and all the edges which are not in G are put in the graph G complement. This figure, of course, becomes much more clear if we put G complement and G over each other and color the edges red and blue. You realize that if you take all the red and blue edges, you get the complete graph. However, red edges are in the graph G and blue edges are in the graph G complement. So, complementing a graph is very simple. You throw away all the edges which were in the graph and you put back the edges which were not in the graph. Now, let's revise the definitions of an independent set and a clique. X, Y in C, and whenever X is not equal to Y, X, Y is an edge of the graph. Thus we observe that I is an independent set in G if and only if I is a clique in G bar. So, when you take the complement of a graph, what happens to cliques and independent sets? Well, all the cliques become independent sets and all the independent sets become cliques. Well, that's quite obvious if you think about it. Remember, an independent set is a set such that if I look inside the set, I see no edges. Now, if I were to complement the graph and look into the same set again, I would see all the edges present there, so it would become a clique. The same applies to a clique. A clique by definition is a set such that when I look inside the set, I see all the edges. Now, if I complement the graph, then if I look in the same set which was a clique before, well, now all those edges would be thrown away and it would have become an independent set. So now the reducibility is easy to come up with. The reducibility is just given by this very simple algorithm which says that on input G, K, output G complement, K. So all this reducibility does is complements the graph. And that's our reducibility. Now, it's easy to see that if G had a clique of size K, then G complement will have an independent set of size K. And if G had an independent set of size K, then G complement will have a clique of size K. In fact, this reducibility does not only shows us that the independent set problem is reducible to clique, but it also shows us the other way around, that the clique problem is reducible to the independent set problem via the same reducibility. So, what we have done is we have been able to reduce the independent set problem to the clique problem. In this case, you will observe that the reducibility was extremely simple. It was almost trivial. In fact, it was trivial. All we did was complemented the graph. Sometimes reducibilities are this easy. Sometimes they can be more challenging and more complicated. But let's see what we have done. We have proved the theorem that the independent set is polynomial time reducible to clique. Consequently, clique is also NP-complete. How do we prove this? We have to give a reducibility. The reducibility simply takes the pair G, K and outputs G complement, K. Clearly, G has an independent set of size K if and only if G complement has a clique of size K. So this finishes the proof of the NP completeness of this very simple problem called clique. What you should learn from this is this simple example. I kept this example very simple. Is when you're trying to prove NP completeness of a problem, you don't know much about which problem to choose to show that your problem is NP complete. You should always try to choose the problem that looks very close to your given problem. Well, let's apply these ideas once again to another graph theory problem and prove that this is NP complete. The next problem that we will discuss is the vertex cover problem. Let us define another problem. First, we come up with a definition. Suppose you have a graph G which is given by vertices V and E is the set of edges. Let's take a subset W of the vertices and we'll call this subset W a vertex cover if all the edges of G intersect W. That is, for all pairs x, y in the edge set, x, y intersect W is not empty. So what is a vertex cover? Let's think about it once again. You have a graph and you pick a subset of vertices of the graph such that all the edges intersect this given set. So every edge is either inside this set or has one endpoint inside this set. In other words, there cannot be an edge which is completely outside this set. Such a set is called a vertex cover in a graph. Let's look at this graph G given to you on your screen. It has 10 vertices. And now if you look at the vertices B, C and F, you realize that these three vertices form a vertex cover in this graph. That is because all the edges in the graph intersect this set. If you look at any edge in this graph, that intersects the set B, C and F. Therefore, this set is a vertex cover. Let's look at another figure that is shown to you on your screen. This graph has 12 vertices, and in this case now I have a set of size 4, A, C, D and F, which is a vertex cover. And in this case all the edges intersect this set, therefore this is a vertex cover in the graph. So vertex cover is a subset of vertices such that all the edges intersect that given set. That's what a vertex cover is. Now what we can do is we can define our computational problem once we have this graph theoretic concept. Let's define the following language. VC, which stands for vertex cover, is going to be the set of all graphs G and integers R such that G has a vertex cover of size R in it. So computationally we have the following problem. We will be given a graph G and we will be given an integer R. We'll have to find out if G has a vertex cover of size R. Well, here I want you to realize one thing. Remember independent sets and cliques. Now, independent sets and cliques have a certain monotonicity property. Suppose that I tell you that a graph has a clique of size 500. Well, then it has a clique of size 499, it has a clique of size 498 and so on and so forth. So if I tell you that if it has a clique of size 500, it has a clique of size, all sizes smaller than 500. That's because if you take a clique and throw away a few vertices from it, what remains is once again a clique. Similarly, the independent set size has this monotonicity property. If I tell you a graph has an independent set of size k, then it has an independent set of size k prime whenever k prime is less than or equal to k. And once again, if you take an independent set in a graph and throw away a few vertices, what remains is again an independent set. The vertex cover problem has the opposite monotonicity property. Suppose that I tell you that a graph has a vertex cover of size 30. Well, then if you throw away one vertex from the vertex cover, you may not be left with a vertex cover. On the other hand, if you start adding more vertices to your vertex cover, well, what you will get is another vertex cover. Thus, if I tell you that a graph has a vertex cover of size 30, then it has one of size 31, 32, 33, and so on. So it has the opposite monotonicity property. Adding vertices to a vertex cover does not destroy its property of being a vertex cover. On the other hand, deleting vertices from a clique again gives you a clique. Adding vertices to a vertex cover gives you another vertex cover. Deleting vertices from an independent set gives you another independent set. So the vertex cover problem is slightly different from the independent set problem. Now, what we want to do is we want to show that this problem is NP-complete. First thing we will have to show is that the vertex cover problem is in the class NP. Once again, I am leaving this part of the proof to you. This part you will do on your own. To show that vertex cover is in the class NP, all you have to do is come up with a very simple polynomial time verification algorithm for this problem. The real thing that we really have to show is that this problem is NP hard. How do we do that? We will reduce a known NP complete problem to vertex cover. Let's see what are the known NP complete problems to us now. Well, we had 3 problems which were known to us, and we have now added a 4th one. The problems that we know are NP complete, that we have ourselves proved or seen a proof of NP completeness, are these 4 problems: SAT, 3-SAT, independent set, and now the clique problem. So we can choose any one of them and reduce it to vertex cover, and that will show that vertex cover is NP complete. So which problem, once again, out of these should we pick? Well, that's the point I'm trying to make in this whole lecture by keeping these problems so simple. These are not difficult problems, but what I'm trying to do is show you how to approach the problem. You have 4 known NP complete problems and you have vertex cover. You would like to prove that one of these problems is reducible to vertex cover. How should you go about it? Well, we can show any one of the following to establish the NP completeness of vertex cover. We can either show that SAT is polynomial time reducible to vertex cover. We can try to show 3-SAT is polynomial time reducible to vertex cover. We can try to show independent set is polynomial time reducible to vertex cover. And we can also try to show that clique is polynomial time reducible to vertex cover. Once again, here you should choose the problem that you think will make your reducibility easy to come up with. So, since once again we are dealing with a graph theoretic question, therefore SAT and 3-SAT are out. They are no longer candidates, at least if we are going to give it our first try. I would stick with independent set and the clique problem because they are both problems in graph theory, and vertex cover is also a problem in graph theory. So what we will do in this case is choose independent set and show that that is reducible to the vertex cover problem. What we want to do now is to think about the vertex cover and independent sets, these 2 concepts, and try to find a relationship between them. We have decided that we are going to reduce the independent set problem to the vertex cover problem. So we should start thinking about these 2 concepts and try to relate these 2 concepts. If we are able to relate these 2 concepts, that would point us to the reducibility that we are after. So let's think about these 2 concepts. Suppose now that you have a graph, and let's take W to be a vertex cover in this graph. So I have a graph and I've picked a particular set W to be a vertex cover in the graph. Now, so here is W. Let me look at all the vertices which are not in W. So the complement of the set W, and see how does it look like. So what I do is I take W, which is a vertex cover, and I take its complement and call it x. So x is v minus w, and that's a set minus there. So I look at all the vertices that are not in w and see what is the condition that says that w is a vertex cover. What does it tell me about x? Well, if I look at any edge in the graph, I know that this edge must intersect w. So x comma y, xy is an edge here, intersect w is not empty. But this is the same thing as saying that x comma y is not a subset of x, which is the same thing as saying that x comma y is not no edge is present in x. So what is x then? Well, x is an independent set. We can think about this same relationship in another way. Here was your set w, and here were all the other vertices which I was calling x. Now suppose if there's an edge here in x, then this edge obviously doesn't intersect w. That means that w cannot be a vertex cover. So if you look at a vertex cover and you see the complement of it, that must be an independent set. So this is the relationship between vertex covers and independent sets. Let's see what we have actually proved. We have proved a little theorem which says that w is a vertex cover in G if and only if its complement is an independent set of G. So now what we can do is we can read this theorem in terms of sizes of independent sets and sizes of vertex cover. If we do that, we get the next theorem that is written on your screen, which says that G has an independent set of size k if and only if it contains a vertex cover of size n minus k, where n is the number of vertices in your graph. So if you think about vertex covers and independent sets, they're complementary objects inside a graph. Every independent set, its complement is a vertex cover, and every vertex cover, its complement is an independent set. In other words, whenever you find a vertex cover of the graph, you've also found an independent set. And whenever you find an independent set in the graph, you've also found a vertex cover. These are two complementary objects inside a graph. Once we have this relationship between vertex covers and independent set, then our reducibility is going to be easy to come by. Let's look at a picture and see this theorem and what we have proved in it. So in this figure, there's a graph G with an independent set in it, which is marked right there. And if we look at the remaining vertices, they make a vertex cover. You'd see that all the remaining vertices, every edge intersect the complement of the independent set. Of course, if we look at the next figure, in which what we have done is separated out the independent set from the rest of the vertices, things become much more clear. The independent set is empty inside, and therefore if there is any edge in the graph, that either belongs to the complement or only shares one edge with the independent set, and therefore its other edge intersects the complement. So this shows that independent set and vertex cover are complementary objects inside a graph. Now we can come up with our reducibility, which is very easy. The reducibility is very simple. Suppose that you get as input a graph G and K. So you are being asked if G has an independent set of size K. Then you will just output G and n minus K. Now, if the graph has a vertex cover of n minus k, then the graph has an independent set of size k, and vice versa. So this is our reducibility. It shows us how to reduce the independent set problem to the vertex cover problem. So the theorem now we have proved is that independent set is polynomial time reducible to vertex cover. Consequently, vertex cover is also NP complete. So we have been able to establish the NP completeness of yet another problem called the vertex cover problem. So here is now the list of all the NP complete problems we have seen so far. The first one is SAT, which is the Cook-Levin theorem. The second one is 3-SAT, by reducing SAT to 3-SAT. Then the independent set problem, which was obtained by reducing 3-SAT to independent set. Then the clique problem, which was obtained by reducing independent set to clique. And lastly, we now have the vertex cover problem, which was obtained by reducing the independent set problem to the vertex cover problem. So this is the knowledge base that we have now gathered. We have 5 NP-complete problems that we know of, 3 from graph theory and 2 from propositional logic. 2 are satisfiability questions, and clique, independent set and vertex cover are 3 problems which come from graph theory, which are NP-complete. What we want to do now is look at another problem in graph theory and prove its NP-completeness. This is an extremely celebrated question. This is called the Hamiltonian path problem, and we will see that once we prove that the Hamiltonian path problem is NP-complete, we can easily establish the NP-completeness of Hamiltonian cycle problems and so on and so forth. Well, you must have heard about this problem previously. As you are a computer scientist, you must have heard about something called the traveling salesman problem. What we're going to do is take a model of that problem, a simplified version of it, and prove that it's NP-complete. Let's recall what the traveling salesman problem is. The traveling salesman problem is the following. There is a map of cities. There are a bunch of cities, and between any 2 cities, there is a cost associated of going from one city to another. Let's say the price of an airline ticket to fly from one city to another. So you have a bunch of vertices which represent cities, and edges which represent flights going from one city to another, and these edges usually have weights on them, that is the cost of buying that ticket. Now there is a traveling salesman, a salesperson that wants to go and sell some things to in all these cities. He has a home, and what he wants to do is visit all possible cities exactly once and eventually come back to his home. However, he wants to purchase the tickets in such a way that minimizes his cost. That thing is called the traveling salesman problem, and it's an extremely famous problem in computer science. Jack Edmonds had said that, well, finding such a cheapest tour is not going to be possible in polynomial time. Therefore, he had conjectured that for the traveling salesman problem, there is no polynomial time algorithm. Unfortunately, if you think about the traveling salesman problem, it's not a yes-no question. It is not a question, it's not a yes-no problem, it's not a decision question, it's an optimization question. The question is to find out of all possible Hamiltonian cycles in a graph, the one which has the least weight. So it's an optimization question. What we will do is, we will look at the decision version of this problem, and we will show that that problem is NP-complete. Once we show that the decision version of Hamiltonian cycle or the Hamiltonian path problem is NP-complete, that would prove to us that if somebody were to solve the optimization problem in polynomial time, they would also prove that P is equal to NP. Therefore, it is extremely unlikely that we can solve the traveling salesman problem in polynomial time. Well, for us to do that, we will have to once again go back to graph theory and revise some concepts for graph theory. So let's do that. Now we will look at another problem, and we'll show that this problem is NP-complete. But in this case, the reducibility is not going to be very easy. Let's first define the problem. So now we will define the problem, and in this case we are going to be dealing with directed graphs. Previously we were dealing with undirected graphs. The clique problem, the independent set problem, and the vertex cover problem were all defined for undirected graphs, but for this particular Hamiltonian path problem, we will move to directed graphs. Recall the definition of a directed graph. In a directed graph, you're given vertices and a set of pairs which we call edges, and these are ordered pairs now. Therefore, the edges have a direction, and that's the only difference. A directed graph, the edges have a direction. In an undirected graph, the edges do not have a direction. So now we have G equals V comma E as a directed graph, and edges are ordered pairs and they have a direction. Here's a picture of a directed graph for you. And now let us define what is a Hamiltonian path in a directed graph. So the definition of a Hamiltonian path is as follows. A Hamiltonian path from S to T is a path in the graph such that it starts with the vertex S and ends at the vertex T. Furthermore, it contains all the vertices of the graph exactly once. So if you have a directed graph and a given vertex S and T, what you want to do is find a path in the graph that goes through all the vertices of the graph and eventually ends up at T. And you're only allowed to visit every vertex once, and you must visit each vertex exactly once. If you can find such a path in your graph, then such a path will be called a Hamiltonian path. So let's look at this figure, and this figure shows you a directed graph, and there are two vertices that I have marked S and T. As you can see, there are vertices in this graph and all the edges have a direction. The question is, does this graph have a Hamiltonian path from S to T? So in this particular case, what you would do is you would try to start from S and follow the edges in such a way that you hit every vertex exactly once and eventually reach T. And the question is that possible or not? If that's possible, the graph has a Hamiltonian path, if you can find such a path. Otherwise, the graph does not have a Hamiltonian path. So let's look at this same figure, and yes, this graph does have a Hamiltonian path from S to T. And what I have done is, in this figure, made the edges that are on the path, that belong to the path, I have bolded them out, so the path has now become clear. As you can see, the path starts from the vertex S, it does go to every vertex of the graph, and then eventually ends at T. So this is what a Hamiltonian path in a graph is. So if I give you a directed graph, some graphs have a Hamiltonian path from a vertex S to T, others don't. For example, I can easily make a graph for you in which from a vertex S to a vertex T, they are completely disconnected from each other. Such a graph would obviously not have a Hamiltonian path from S to T. Now, the computational question is, can we tell if a given graph has a Hamiltonian path from S to T? So suppose if I give you a graph G and two vertices S and T and ask you if there's a Hamiltonian path from S to T, can that question be answered in polynomial time, or can that question be answered by a polynomial time algorithm? That's the computational question. So let us define the Hamiltonian path problem formally. Let's define Ham path to be the set of all graphs G along with two vertices S and T such that the graph G has a Hamiltonian path from S to T. Thus, the computational question is, given a graph G and two vertices S and T, does there exist a Hamiltonian path from S to T? What we will do is, we will show that this problem is also NP-complete. In order for us to show that the problem is NP-complete, remember that the first thing we have to do is show that this problem is in the class NP, which amounts to showing that there is a polynomial time verification algorithm for this problem. Once again, as I've said, usually this part is very easy, which is also the case this time. It's very easy to come up with a polynomial time verification algorithm for the Hamiltonian path problem, and therefore I'm leaving that part for you to prove. What we will do is now concentrate on showing the NP hardness of this problem. The way we will show NP hardness of this problem is, we will show that 3-SAT is polynomial time reducible to Hamiltonian path. Consequently, the Hamiltonian path problem is also NP-complete. Remember that what I'm doing here is something that I told you we are not going to do. Remember, we have a knowledge base of known NP-complete problems. There are 2 from Boolean logic or propositional logic and 3 problems from graph theory in our knowledge base. We can reduce any one of them to Hamiltonian path to show that Hamiltonian path problem is NP-complete. Now, Hamiltonian path problem itself is a problem from graph theory. So it may seem to us that the other problems, the other 3 problems which are from graph theory are closer to the Hamiltonian path problem. But sometimes that's not the case. Although it is possible for us to come up with the reducibility from these graph theory problems to the Hamiltonian path problems, it's much more natural to come up with a reducibility from the 3-SAT problem to the Hamiltonian path problem. Remember that in theory, once I show that satisfiability is polynomial time reducible to Hamiltonian path problem, then I show that Hamiltonian path problem is polynomial time equivalent to all problems in the class NP-complete. Thus, all NP-complete problems will be reducible to it. And this would mean that it is possible to take any NP-complete problem and in theory reduce it to the Hamiltonian path problem. But what we want to do is we want to come up with a reducibility that is easy, natural and clear for us to understand. This reducibility that I would show you today is not going to be very easy. In fact, I think it's a very ingenious reducibility that shows that the 3-SAT problem is polynomial time reducible to Hamiltonian path problem. Let's see what we have to do in order for us to come up with this reducibility. Well, if we recall the definition of the reducibility, we'll have to do the following. We'll be given a Boolean formula phi and we will define a graph G sub phi and 2 vertices S and T in it such that G sub phi has a Hamiltonian path from S to T if and only if the formula phi is satisfiable. So, given a formula phi, we will construct a graph G sub phi such that if phi is satisfiable, then G sub phi will have a Hamiltonian path from S to T. If G is not satisfiable, then G sub phi will not have a Hamiltonian path from S to T. Notice that we have to also make sure that the graph G sub phi can be computed from phi in polynomial time. What is ingenious in this particular reducibility is the definition of the graph G sub phi. I will define this graph G sub phi in terms of the formula phi. And once I've come up with the definition, you would be easily convinced that you can take a formula phi and construct this graph G sub phi in polynomial time. And therefore, this is a polynomial time reducibility. Notice that what we need to do is translate once again. What we're doing is translating a satisfiability question into a Hamiltonicity question. So we are taking the language of satisfiability and translating that problem and turning it into a graph theory problem. If someone wants to know whether phi is satisfiable or not, we turn the problem, we translate the problem and make a new graph, and now the question has been reposed as saying whether this graph G sub phi has a Hamiltonian path from a given vertex S to T. Well, in the next lecture, we will formally define this graph and prove that this graph has the properties that I have been telling you about. Then I will also convince you that G sub phi can be computed in polynomial time from phi. Once we do that, we will establish the NP completeness of Hamiltonian path problem, and then we can go on to prove that related problems to the Hamiltonian path problem, such as the Hamiltonian cycle, undirected Hamiltonian path, undirected Hamiltonian cycle, are all NP complete. Well, we've run out of time, so all these exciting results will be presented in the next lecture. I'll see you next time. Thank you and goodbye.